Alright, in this video we'll be looking at some properties of the expected value, particularly when dealing with multiple random variables. So let's take two random variables x and y who could give you all these numbers here. And now suppose we have a new random variable whose job is to add up whatever x and y happen to land on. So every time you reach into this new magic box and ask for a number, he quickly calls up x and asks x to give him a number, right? He calls up y as well and asks y to give him a number. Gets these two numbers, he adds them up, then hands you the result. So here he would get 9 plus 10, which would be 19. The 8 plus 5 would be the 13. 7 plus 4 would be 11, 5 plus 20 would be 25, 8 plus 9 would be 17, 6 plus 18 would be 24. I think you get the idea here. The important thing is where those numbers are coming from, right? It's a new random variable who's adding up two separate other ones, right? And you might be wondering, well, what's the expected value of this x plus y guy? Well, the expected value of each of the x and y boxes can be thought of as some long-term average of whatever they individually spit out. So the long-term average of what x plus y spits out would just be the sum of those two individual expected values then, right? The average of the sum should just be the sum of the averages. So we can write e of x plus y as e of x plus the e of y. Right, and now if we do something a bit sneaky here, if we change all the y's to another copy of x, right, we find that the expected value of two x's is just 2 times the expected value of the 1x. And that seems to make sense, right? If you double all the numbers that a box is spitting out, right, well then you'll double the average value as well, right, in the long run. So you'd hopefully agree that this sort of scaling happens not just for 2, not just for doubling, but for any constant number multiplying. So any constant multiple scaling the random variable inside the e bracket can just hop outside like that. And it's going to be very useful for what we do later, but first we can use this to think through a question like this one. How many 4s would we expect if we rolled a die 12 times? Okay, so we're really tracking a random variable here, which we can call x. Every time you ask x for a number, he'd roll the die 12 times, count up how many 4s he got, and give that result to you. Right, and let's first think about this without any of the formalism, because I'm pretty sure this question you could answer right now without any of our language, right? So here are the 12 die rolls with these 12 little green boxes here, and the possibilities can be visualized by listing each of the possibilities from a single die roll, the numbers from 1 to 6, right? And each box is the same size, because for a normal die, the 6 outcomes are equally likely. Then we can picture rolling the die 12 times as distributing those little green boxes at random, say like this. Then we can see how many rolls landed inside the 4 box, which would be these 3 here. So if we're asking for the expected number of 4s, well, what we'd expect is that for a fair die, the distribution is even, giving 2 rolls that landed on 4. And again, this wouldn't be a literal real-life expectation. I mean, it's possible this time, but it would be quite remarkable for it to actually be perfectly even like that in real life. Okay, but again, this is mathematically what we would theoretically expect. So the calculation that would get us there would be just to multiply that probability of 1/6 by 12, the number of times we rolled the die, and the answer would be 2. And there is absolutely no problem whatsoever in thinking this way. It's the clearest way and the absolutely correct way to think about it, right? But I just want to show you that this is consistent with the idea of expected value that we've been playing with, right? Because I don't think it's obvious that those two are really the same thing. It makes sense that we'd expect 2 4s, right? But why is this consistent with our present definition of expected value? Okay, and so let's go with that. Previously, what we said about expected value is that you should multiply each possible outcome with the probability that it happens. the way we've defined our random variable here, this isn't actually that easy. Okay, because let's say we want the probability that this big X, how many 4s he sees, let's say that has to equal 3. Okay, that means we need to have 3 of those die rolls land on the 4. But which 3? So we start by working out how many possibilities there are there. Which 3 of those 12 rolls will land in the 4? Now that's done in 12 choose 3 number of ways. Okay, then they actually have to land in the box. The probability that happens is 1 out of 6 for each one. So to hit that all 3 times, it would be 1 out of 6 cubed. The other 9 rolls can then go anywhere else, but it's important they have to miss the 4. So that happens with 5 out of 6 chance for each one, giving us 5 out of 6 to the 9. Right, so it's pretty complicated. I want you to see that, right? And doing that calculation for all possible values of X, right? I guess that would have to be from 0 all the way through to 12, right? I guess that wouldn't be too hard because it follows the same pattern, but it would be quite long and tedious to do. Okay, now there is a way to simplify this process though, using the properties of the expected value that we just saw previously. Alright, because rather than think about all 12 die rolls at once, let's think about only one of them. Might seem silly at first, but we'll define a new random variable y that counts the number of 4s he sees from only rolling that one die. Now the outcomes are really easy then. It can only ever give you 0 or 1, right? 0 if it misses the 4, which happens with probability 5 out of 6. 1 if it hits the 4, which happens with probability 1 out of 6. Okay, so the expected value of this one is pretty easy. You multiply the 0 by the 5 out of 6, then the 1 by the 1 out of 6, then adding them up gives you, of course, just 1 out of 6. Right? And of course this expected value will always just be the probability of that outcome you're trying to hit. Right? In our case, the 1 out of 6 was precisely the probability of hitting the 4, okay, but only for a single roll. How does that help us? Well, X is the number of 4s we get from 12 rolls, not just one. But we can think of X in a bit of a different way. Right? When we ask him for a number, rather than roll all 12 dice by himself as quick as he can, right, he can just ring up Y. He can ask Y to roll a die for him. But Y only rolls one die. So he'll go, hey, do it again, right? He'll ask Y to do it again. Right, then again. And if he can convince Y to repeat his experiment 12 times, well, that's the same thing then. He's rolled 12 dice. Okay, so he can just total up what Y tells him all 12 times, and he can just give you that number instead. Right, so in fact, the random variable X is literally 12 copies of the random variable Y. And we can even write then that X is 12 times Y. And we just saw that this 12 times, this constant multiple, can fly outside the bracket there, right? And we just worked out the expected value of Y. That was a really easy calculation. That was just 1/6. Okay, and so that gives us the same calculation as before, 12 times 1 over 6, which is 2. Okay, but I hope what you can take away from this is that by using those properties of the expected value that we saw before, we can actually sidestep a lot of that hard, tedious work and treat X, who was a rather complicated random variable, as a combination of easier random variables. Okay, so in our case, just a bunch of copies of Y, which was a very easy one to deal with. Okay, now again, I actually prefer you to think in the first way. All right, the first thing we did with dividing up the roles into their little boxes, that I think was nicer, right? This was purely to show you that our new notion of expected value is just an extension of that, right? They're perfectly consistent definitions, right? And like we said before, our new formulation allows us to work with more complicated random variables and probability distributions, right? This was just a special case where you're repeating the same experiment over and over again, right? But it's worth mentioning, so let's just write that out properly now. Okay, so suppose a random experiment has exactly 2 outcomes, and we'll label those 2 outcomes as some kind of success and failure condition. So in our case, the experiment was rolling a die, success was rolling a 4, failure was missing the 4. Okay. Suppose also that the probability of succeeding is this little p here. So for us, little p was the probability of successfully hitting the 4, which would be 1 out of 6. Then the probability of failing must be 1 minus p. Okay, must be everything else. Since those probabilities have to add up to 1, then the chance of failing has to be 1 minus p. If we repeat this experiment n times, so in our case, n would have been 12 times, right, because we rolled the die 12 times, then let x be the random variable counting how many successes we saw. So in our case, x counted how many 4s we hit within those 12 rolls. Then we saw that x follows what we're going to call now a binomial distribution, right? And what we calculated was that the expected value of x is just the number of times you try the experiment multiplied by the probability of each one succeeding. Okay, now something to try, and we almost got there already, right, is working out the probability mass function, right, the little p function, right, the probability that the big X equals any given value of little x. I almost gave you a complete example in the dice thing, right? It will involve your binomial coefficients, right, your n choose somethings, and which is, I guess, why it's called a binomial distribution, right? But we'll leave that there for now, right? So thanks for watching, and I'll see you next time.